begin with Joshua Qualls, our own NTU here, so just take it away.
All right, thanks. I'd like to thank the organizers for putting together this workshop, giving me a chance to talk to you guys about some stuff I've been working on lately. This is based on work to appear with Al Shapir. So when it appears is a good guess. Any suggestions would be appreciated. To appear when we run out of things to do with it, I guess is what I want to say. So, I want to talk to you about a couple of cute little things we've been doing. Word of the day is bootstrap. So there will be no localization or Chern-Simons, or I think I saw a brain in the talk earlier, but I have since removed it. I want to keep things on the up and up. Two things I'm going to be talking about specifically are some interesting entropy bounds that we have found using the bootstrap program. Before moving on to some hints of things to come that we found while trying to test some of these bounds that we've found in previous works. In particular, we're testing these bounds using Lorentzian lattice CFTs. The motivation for such work doesn't matter. Pick your own. I don't care. There are the obvious things like condensed matter, applications, or statistical physics. What I'm going to have in mind is some sort of quantum gravity that we can define via ADS through CFT2 using the typical sort of correspondence between central charge and ADS length. But, well, I'm among friends, so that's really the motivation, right? We're looking at things with ADS CFT in mind. But if I were giving this in front of a more general audience, I would try to downplay all of those amazing applications. So I said the word of the day is bootstrap. In particular, I've been working at the Conformal bootstrap program. When I say that, I am talking about constructing conformal field theories using nothing but consistency, conformal invariance, and unitarity. There's been a lot of success in many different numbers of dimensions, 3D, 4D, 6D, using crossing symmetry of some of these 4-point correlators or more complicated correlators. Some interesting work in super conformal bootstrap happening lately. I'm not going to talk about any of that stuff. I'm going to talk about two dimensions. In the long, long ago, maybe back before I was born, which is sort of weird to think about, people studied 2D CFTs with small central charge, C less than 1, to the point where we found a complete classification of some of these rational CFTs or minimal models. Again, not going to talk about any of that stuff. I'm going to restrict myself to 2D CFTs with C greater than 1. Pretty unknown theories for the most part, actually. Right? We don't have such a complete classification. So, for such a simple object, it's sort of weird that we're so in the dark about a lot of these things, and we hope to fix that. All right, my particular way of applying the bootstrap program is to use modular invariance of the partition function. So in spirit, this is like the 4-point crossing symmetry. In fact, it's actually complementary to it in the higher dimensions. I'm not going to worry about that, though. When I say modular invariance, I just mean invariance of the partition function under the modular transformations. Good old modular group P, SL2Z. Generated by two transformations, the S transformation, the T transformation. There's some obvious simple consequences of modular invariance. For example, T invariance gives you this condition on the conformal weights. S invariance is what led Carty to write down this famous Carty formula. More recently, Hellerman, who laid the groundwork for a lot of the things that we've been doing, used S invariance of the partition function to give a bound on the conformal dimension delta 1. It's the smallest conformal dimension, non-identity. So, inspired by that, we started to look at larger conformal dimensions. And in terms of the old results, things that I might reference, we found bounds on conformal dimensions delta n. Right? You pick an n, and I give you a bound on that conformal dimension. And all you would need to know about the how of that process was that we turned this modular invariance condition invariance under the S transformation into differential constraints in the partition function. Right? Taking successive derivatives of the partition function evaluated at the self-dual inverse temperature beta equals 2 pi. With some nice assumptions like discrete spectrum and unitarity and those sorts of things, we can turn those differential constraints into polynomial constraints. And then by taking convenient ratios of these polynomial constraints, we can find things like sum rules or positivity conditions that we then use to do proofs by contradiction, sort of very similar to what things are happening in 4D or whatever else. Right, so the result was that we found a bound going as delta n less than or equal to C total over 12. That's a total central charge, C left plus C right. So long as the n in our delta n obeys this equation. As far as we were able to tell, that is just a relic of our method of proof, or at least that's what it seemed like initially. If we assumed this, then we could derive bounds on delta n all the livelong day. However, no, I'll talk about that in a second. If you're gravity inclined, these upper bounds on conformal dimensions are just going to map to upper bounds on masses in some sort of bulk gravitational theory. So what we realized was that so long as this condition is satisfied, we can bound in primary operators in this sort of way. Okay? So we can derive a bound on n such primary operators so long as this is obeyed, which means that there must be at least n primary operators that are obeying this inequality. Right? We're turning the fact that we can derive these things into an existence claim on the minimum number of primary operators that are going to satisfy this sort of inequality on the conformal dimension. Right? So we conjectured a lower bound on the number of states satisfying this bound. Later paper by Hartman, Keller, Stoica gave an independent argument that confirms that this is in fact a lower bound on the number of states in the class of theories that we consider. So, having found that lower bound, we then asked ourselves, could we find an upper bound? I'm going to very briefly talk about the techniques and the results, compare it to some other results, particularly that those previous authors found. Yes?
The mass of the first black hole, is that C by 12? C by 20?
So it is C by, it depends on what you mean by C or C total, but it goes as 1 over 8 G Newton. And C over 12 corresponds to 1 over 4 G Newton. So it's twice the mass. Twice the mass of the lightest spinless BTZ black hole. Which is very suggestive, right? And sort of motivated some of the work that follows. Surely we could lower that. We're going to consider nice 2D CFTs, discrete spectrum, unitarity. For purely imaginary modular parameter tau, these partition functions reduced to the thermodynamic partition function. I didn't introduce a degeneracy factor here, so I'm explicitly summing over all of the energies. Right? Many of the terms in the sum, in fact, you would expect that many of the terms in the sum are going to give identical contributions. That's fine. We'll just deal with it if we need to. Now, these differential constraints that we had previously used, sort of in the full bootstrap program, are also going to apply to this simpler thermodynamic partition function. And that's nice. It's going to give us much easier to handle constraints. In particular,
sorry, the bounds you just mentioned is also satisfied by the minimum models?
Yes, yes.
Okay.
Yeah. Well, yeah. If you tensor together minimal models, see, the bounds we derived are only true for that class of CFTs where the central charge is bigger than 1. But when you just start to think of a minimal model, you get central charge less than that. So, and you say, well, to get it bigger, we just tensor together, various copies of minimal models. But then you're still going to find some primary operator that's maybe living in only one of the tensored copies, and so it'll definitely fall below. All right, so applying those differential constraints is now going to give us these new polynomial constraints. All right, And they look like this. We have some polynomial GP, weighted with the exponential, sum them all up and you get 0. You can find explicit expressions for these polynomials G. They're related to polynomials that are known as the Bell polynomials, which, you know, just polynomials found a couple of hundred years ago by mathematicians who were looking for interesting things to study. We only need to focus on the lowest order constraint, p equals 1, which takes the following form. In order to proceed, we define some energies. We just split the sum basically into its positive and negative contributions, right? And then carry all of the negative terms in the sum over to the right-hand side. So you get an expression that's like this. Right? Positive energies, negative energies. I should say non-negative energies and negative energies.
Negative energies are because of the 0-point shift.
Yes, exactly. Didn't specify that, but our ground state energy is going to be minus C total over 24. No, that's very good, very good. Thank you. All right, at this point, we're going to play the game where we try to bound each side of this equality, one above and one below, and then see what sort of statement that gives us. In particular, every term on the right-hand side is going to give a contribution less than if we were to evaluate it at the ground state energy. Right, so we can replace this sum over all these states by just this multiplicative factor p times the argument of the sum evaluated for the ground state. All right, the left-hand side is a little trickier. That's sort of a relic, and I don't need to worry about it due to time. But effectively, on the left-hand side, this is a plot of what the argument of this sum looks like. And so to proceed, we would like to say pick some cutoff energy curly e. Here, I picked it at around 5 for value x, where x is 2 times pi times the energy. All right, having proceeded to pick some cutoff energy E, we will only consider the states that are going to be under this curve between cutoff energy E and whatever the corresponding value is on the left-hand side, over close to 0. So we're going to be dropping terms from this infinite sum on the left-hand side, but that's fine. Right, because I'm trying to bound it, trying to find something smaller than the left-hand side. So not a problem. We'll just throw away some of these things that come from the infinite sum. Okay, so what happens is the right-hand side is less than or equal to this expression p. The left-hand side is going to be greater than or equal to the contributions of some number of states. We'll call it NE times the argument of the sum. And we have this inequality. This is cute. NE's counting the number of states between this expression and that cutoff energy E. P's the number of negative energy states. We could do better. For example, we could add a factor of, to keep you guys on your toes, apparently I'm just going to change my terminology all the time through this talk. We're going to change P to N. We could add a factor of N to both sides. So after dividing this through and adding an N, we then get a bound on the total number of states up to some cutoff energy E. Say for this little sliver near the origin, so if we want to pick that up, we're just going to take this cutoff energy E to be large. How large? You tell me. Make it as large as you want. At which point we're getting an approximate upper bound on the number of states up to some cutoff energy E. Okay? An upper bound on the number of states, clearly also an upper bound on the number of primaries. And so we therefore have an upper and lower bound on the number of primaries in this class of 2D CFTs. For large central charge, we could go ahead and take a log of N on both sides. And what that'll give us to leading order, okay, we have pi c on 12, we have this cutoff energy contribution. We got this term, but a point I'm glossing over is that curly E will be bigger than 1 over 2 pi. So this thing is never going to contribute larger than log of C. Log enough C, it's subleading. And so we get something like pi c on 12 plus 2 pi curly E plus some log N. N is the number of negative energy states. Right, that compares favorably to recent results in the literature in terms of calculating what, say, the entropy looks like for this kind of 2D CFT. In particular, this paper that I've mentioned by Hartman, Keller, Stoica, they make the assumption of what's known as a sparse light spectrum, which just says we don't actually want to have to deal with any contributions like this. we're going to say the light spectrum, that is the spectrum of any energies that would contribute to this term, is small. It's subleading, right? And if we are to also make that assumption in our work, then this term would also be subleading. You see that to leading order, we have, roughly speaking, an entropy is less than pi c on 12 plus 2 pi e. These cutoff terms. It's cute. In the interest of time, I'm not going to go through all these details, but because we're trying to find bounds on entropy, we can also make statements about the free energy. It results in, again, an upper bound on the free energy for the class of theories that I've mentioned, which, again, compares favorably to results in the literature. They actually find two leading order, assuming a light sparse spectrum, something that goes to C total over 12 times the max of these two quantities, excuse me, beta and the inverse of beta under that S transformation. And we find the same thing. And I will only mention that, glossing over, I did say that an upper bound on the number of states will also be an upper bound on the number of primaries. Well, we could have approached this and found an honest-to-goodness bound on the number of primaries. And it does take approximately the same form. Check out the paper if you want the nitty-gritty details. We do not use the thermodynamic partition function for this case. We have to use the full partition function in terms of these Virasoro structure representation variances. Eta functions. So if you like eta functions, you should check out appendices A through B. No time. So that brings us to the second part. We found all this stuff, and to be honest, got scooped a little bit. That's what we get for talking about neat things. Oh no, what am I doing talking to you guys about these neat things? I need to publish tomorrow. Anyway, after finding some of these bounds, we didn't really feel like there was enough. We needed to add to the work that we've done, so we decided to try to construct conformal field theories as a means of testing the bounds that we have found and the bounds that other people found. The way we're going to do that is by considering what we call Lorentzian lattice CFTs. All right, now it was previously shown by a guy named Witten that he showed by studying factorizable, holomorphically factorizable CFTs, he found a bound on the lowest primary operator that goes as 1 plus the minimum of C over 24, or C bar over 24. Or if you prefer, you could write it as C total over 48 plus 1. That's a darn good bound. It's quite a bound, but then again, it's quite an assumption. There's no reason to think that all of the CFTs of interest should be holomorphically factorizable. So our dual motivation, the hidden motivation, was to see if we could show that our class of bounds is truly more general, more applicable than this Witten bound. Right? All of the theories we know end up being ones that saturate this bound because, as I said, more general theories are not well known. They're hard to play with. I won't do the lowest things.
That bound exhausted the power of modular variance, but almost none of the CFT have been shown to exist.
Yes, and actually, hopefully I'll get to the point where I say I think even if some of the CFTs exist, their gravitational duals don't, in the sense that they wouldn't be nice theories of gravity.
There's no reason to expect gravity to be due to holomorphic factorized theory. I think that's
no, it's not, and we are going to abandon that very soon. It is, you're right, it's quite restrictive. There's no reason to think that. So we take our inspiration from toroidal compactification and string world sheet theory. I want you to think free bosons on some sort of Lorentzian torus. Right? I'm going to compactify on some interesting torus, see what kind of conformal dimensions I get, see what the number of states look like. The only thing I want to mention here is that rather than working with some bizarre lattice directly, we're instead going to use this Narayan parameterization where we will parameterize our lattice by background fields G and B, exactly what you'd expect, antisymmetric and symmetric, respectively. Then we can express our partition function in the form that looks like this. Right? Our conformal dimension would be the sum of this weight and this weight, where P left and P right are expressed in terms of those background G and B fields. Right? Then our conformal dimension will take the form shown here, where we have this inner product between, and because we're using this nice parameterization. W and K being winding and momentum modes are going to take integer values. And this curly G inverse is going to be something strange that depends on the G's and B's. So the results. Well, in the simplest case, when we did a vanishing B field, which would correspond to holomorphic CFTs, we found that the largest we can make delta 1 is something like 1 over square root of 3. Right? By turning on these B fields, we found a nicer lattice for compactification, where we found a smallest conformal dimension delta 1 corresponding to 2/3. Right? That's an improvement, I would say.
What central charge are you working with?
Sorry, I didn't specify, but the lattices are gamma n comma n. So we have n left moving and n right moving free scalars. So when I say n, the central charge is 2n. So here the central charge is 4, which is where I get these inequalities from. I've actually compared them to the bounds. We see that the bounds going to C total over 12 are closer than these large Witten bounds, but obviously there's no violation here. We would need to consider higher theories. So the punchline is that we need to go all the way up to 24 dimensions, where this fantastic Leach lattice is, which is what motivated Witten's original bound. And we find that, well, to be honest, we're not sure what we find. There are quite a lot of potential vectors that could be the shortest in these 24 dimensions. So far, we've been doing a combination of random sampling and sort of a method of steepest descent guiding things. And as far as we can tell, we have bounds corresponding to, we have conformal dimensions corresponding to delta 1 equals 4.
But don't we know the partition function of the Leach lattice exactly?
We do know the partition function of the Leach lattice, but we have now turned on these B fields as well, which is sort of the trick, right? We're trying to explicitly consider non-holomorphic fields. So yes, in that case, we do know uniquely delta 1 equals 2 is the smallest conformal dimension. It seems as though delta 1 equals 4 is the case for non-holomorphic. What breaks it is that although in all of the SUN cases that we considered, we did get this improvement, in the non-holomorphic case for the E8 lattice, we did not get an improvement. Right, so it's not enough to just sort of gut feel it. We really sort of need to give a better argument, which is what's happening right now. We're sufficiently motivating the result.
That 4 is twice 2, you feel is significant? That
So,
was your, right?
Yes, and what we actually, so when we did the SUN sort of Cartan matrices as our background G fields, what we found was that the minimum length squareds were squaring. We were getting a squared improvement. So we went from 1 over 3 to 2 over 3.
How close does it get to your bound? This seems to saturate your bound, right?
It comes very close. So C total over 12 would be, well, 2 copies of 24 is 48, over 12 is 4, plus a small numerical constant is about 0.4. So we get 4.4, which is obeyed, and it definitely violates Whitney's bound, which is saturated by this. So I will stop there, but please come and talk to me about this. I have so many more amazing lattice CFT things to tell you. Otherwise, thank you very much for your attention.
Thank you. Thank you, Josh. So we'll have time for one question. Questions? Quick ones?
So when in the larger lattices, do you get close to saturating your bound? In these SUN?
So in the SUN case, what seems to be happening is the largest, I'll just do non-holomorphic because it's the interesting one. No, what happens is for SU n plus 1, you get largest conformal dimension delta 1s going as roughly n over n plus 1.
N over n, so constant.
So it's approaching 1. Yeah,
That's
no matter how
very
large
far
you take
from
it. Yeah, we're not. So we saw that pretty quickly that increasing in was not getting us close. That's why we switched to these exotic lattices. And we've sort of extended it to some the other extremal self-dual lattices, which is what I'd hoped to talk about, but I'm not too sad that we didn't get to. Just talk about it next year.
One more thing.
Yeah.
Do you have any example of a theory in which the delta 1 becomes parametrically large?
No. No. Even considering the larger values of k in the extremal self-dual, we do not get that. And we found some interesting things because we were also exploring these entropy bounds. And for that, it's sort of counting lattice points rather than.
So it's possible that as C goes to infinity, it's possible as C goes to infinity, delta 1 cannot become parametric.
Yes, it's possible. Yeah, we've certainly seen no evidence to the contrary. Thank you.
Okay, so next we'll have the next speaker, Kazumi Okuyama.
First of all, I'd like to thank the organizers for giving me the opportunity to speak here. And I'd like to talk about non-perturbative effects in M theory. But of course, this question is quite difficult to study because we don't know how to compute such non-perturbative corrections from first principles. But if we focus on a very special type of vacuum, the ADS4 times sub-7 manifold, we can use holography and consider the dual field theory as the non-perturbative definition of the theory. For example, the famous ABGM is graphically developed in theory of ADS4 times S7 as the K. And we don't know how to compute the quantum corrections on the bulk gravity side, but we have a very definite field theory, Lagrangian description of the theory on the field theory side. So we can, in principle, compute various quantities on the field theory side. In this talk, I will consider mainly the partition function of 3-sphere. And this 3-sphere naturally appears in this context because the boundary of ADS4 in Euclidean signature is the S3. So partition function of 3-sphere is natural quantities to consider in this context. And as you heard from yesterday's lecture by Sanjay Lee, this quantity can be computed by applying the localization technique. So we have a very concrete expression for this 3-sphere partition function. And after applying the localization technique, we get this kind of finite dimensional integral expression of this quantity. This is just the ordinary integral with n variables. This almost looks like the matrix model integral, but this measure factor is not the usual Vandermonde, but something else, which is called Cauchy determinant in this case. But anyway, this is a very concrete expression, so we can, by studying this quantity very carefully, we can learn something about interesting thing about M theory. So in this sense, this model can be thought of as kind of Ising for the M theory. And you're interested in the large M behavior of this quantity. And we can apply the sum point approximation in the large M limit. And I can show that the free energy scales like n to the 3 halves of the large M. And this is consistent with the computation on the gravity side. And this also reproduces the expectation that the number of degrees of freedom of n and 2 branes goes like n to the 3 halves. This is the leading term in the large M expansion of free energies. So there are a bunch of correction terms. And especially we are interested in the exponentially suppressed corrections coming from the instantons in the theory side. And to study such instanton corrections, first we have tried to evaluate this integral exactly at finite n, from small n up to certain relatively high n of order 40 or 60. And here's the example of the result of the exact value of the partition functions of the AVGM at level 1. This is the partition function of m equal to 1, n equal to 2, and so on. And as you can see, this is just a number, a finite number, and some combination of pi and some integers or something.